Alright, welcome to this Chapter 9 video on converting to standard form for Algebra 1. We're going to briefly go through something that we've already done earlier in the year. When you did it earlier in the year, I didn't actually tell you what it was useful for back then. I just said this is a technique that is important to learn how to do, and that we'll be using it a lot later in the year. And so now finally we're at that point where we're going to use it. So the idea is foiling or rectangle diagramming or distributing when you have binomials multiplied by each other. And the reason we're going to use it is for quadratic functions. So we've already learned how to square numbers, so it should be pretty simple. So if you have something like 5 squared, we learned that that's just 25. Super easy, right? Okay, so squaring numbers is very basic. Just take the number, multiply it by itself. If you're squaring a numerical binomial, so numerical just means there's no variables in it, and binomial means that there's two parts. So remember, a polynomial is a sum of many terms that have only positive exponents. A binomial has 2 terms, a trinomial would have 3 terms, etc. So squaring numerical binomials is something like this. Say you have 10 plus 7, and it's the whole thing squared. A lot of you guys are tempted to be like, oh, well 10 squared is 100, plus 7 squared, 10 squared plus 7 squared, that's 100 and that's 49, so this must be 149. And I know it's really, really tempting to do that, but it's completely wrong. And the reason is you have to follow PEMDAS. What you try to do is you try to square these guys first and then add them, but the parentheses mean you have to add these first and then square it. So actually it's 17 first squared, and 17 squared is what? 225, 256. 289. Okay, so it's a really big difference, as you can see, between the answer that you would get if you did it incorrectly and the correct answer. So the last thing I want to talk about, just to kind of give you the introductory idea or refresh your memory, is squaring variable binomials. So now you have something with variables in it. Say you've got x plus 3 squared. Many of you guys are tempted to write, oh, this must be x squared plus 9. But again, just like before, you can't square the two things separately and add them because of PEMDAS. You have to add them first and then square it. But since there's no way to add an x and a 3, we have to do this a different way. And the way that we're going to do it is we're going to show something squared just means it times itself. So this is x plus 3 times x plus 3. And now how you solve this one is up to you. You can use FOIL, you can use rectangle diagram, or you can use distribution. Personally, I like distributions. I go, which is really FOIL. So first times first, x squared. First times last is the outers, so plus 3x inners plus 3x, and last plus 9. It's important that you show your work so you can make sure that you connected all the possibilities. And now we can combine these two in the middle to be x squared plus 6x plus 9. Okay, so as long as you remember that when it's a binomial squared, you have to write it out times itself twice, you can do it with no problem because you have all those other techniques. But now, I think I've shown you this before, but I'm going to show it to you again. There's a perfect squares shortcut. So anytime you have a variable plus a number squared, you're always going to get the same kind of general result. And you can kind of see the example I just did is a formula matching this one. The first term was always x squared because it was x times x. And the last term was always the last two things, the last number times itself, because the last number squared is 9. So n squared is n squared. The part that you miss when you try that shortcut that doesn't work, which is just distributing the 2n, is you miss these middle pieces that are called cross terms. And the middle pieces, it's always inners and outers. And the inners and outers is always x times whatever the number was. And you always do it twice, once for the inners and once for the outers, and then you add them together. So n times x is what you get, and you do it twice, so 2 times n times x. So whatever that number is, you're going to double it to get that number. So if you want to apply this formula, let's do one more example, like x minus 6 squared. You could, and you're always welcome to write it out, x minus 6 times x minus 6, and then do it the long way. But you can try the shortcut here, x squared plus 2 times n times x. Well, my n is negative 6, so twice that is negative 12. So negative 12x plus negative 6 squared is 36. And so you can really quickly and easily go straight to the answer. Okay, and it's really important to notice that for a perfect square, the last number here is always half the middle number squared. And that's because half the middle number is the last number. So there's a close relationship between these two numbers based on the fact that it was starting off as a perfect square. And that's important when you're trying to factor them. So that's our next topic. Working backwards. So we learned about factoring quadratics. Sometimes you have a general factoring, but then there are examples where it's just a perfect square. So if the last term is equals 1/2 the middle term squared, and the first term is x squared, then it's a perfect square. Basically, if it matches that resulting formula, you can work backwards and write it as a perfect square. Then it is a perfect square. Okay, and so let's give a couple of examples. So say you've got x squared plus 10x plus 25. And you want to see, is this a perfect square? So you take half the middle term and you square it. So half of 10 is 5, and 5 squared is 25. So we know this must be a perfect square. And it's a perfect square. The first term is x. The last number squared equals 25, so the last number must be a 5. Okay, so we can check it. The middle term is twice as much as that one, and the last term is that one squared. Let's do one more. X squared minus 14x plus 49. So half the middle number is negative 7, and negative 7 squared is 49. So we get x minus 7 squared. So if they have this property where the last number is equal to half the middle number squared, then it's a perfect square and you can write it as such. And that's really helpful when you're converting to vertex form, which we'll talk about kind of in the future. But for now, I just put this in this section because it correlates with this definition of what a perfect square is. So we're going to do a lot more with factoring in the next lesson, but good to keep this in the back of your mind. Okay, the last thing for this lesson is multiplying non-perfect binomials. So if I come back to the first slide here, when you're multiplying a perfect binomial, this right here is an example of a parabola that might have been in vertex form. So when you're converting from vertex form to standard form, you're oftentimes going to have a parabola in this form. But when you're converting from factored form, you might have a parabola, let's y equals x plus 3 times x minus 6, something like that. Right, so it's definitely still two binomials multiplied together, but it's no longer a perfect square because the two binomials are not equal. But the way that you do it is still going to be the same. There's just no shortcut. So you need to multiply using FOIL, or distribution of rectangular diagrams, firsts, inners, outers, and lasts. And you can get x times x is x squared, 3 times x is plus 3x, negative 6 times x is negative 6x, and 3 times negative 6 is negative 18. And then you combine the two middle terms, just like you always do with FOIL, and you get x squared minus 3x minus 18. So if you're multiplying binomials that are not perfect squares, you have to use FOIL or rectangle diagram. You can't use a shortcut. Oh, you can't use the other shortcut that we just talked about. There are patterns that you can find and follow within multiplying FOIL and binomials, such as the middle number at the end is the sum of these two numbers, and the last number at the end is the product of these two numbers. And when we learned about factoring quadratics, that was one of the properties we used to help us factor them to undo what we had just done. But we'll get to factoring a lot more in the next section again. I just want to point out, this is in factored form. And when it's in factored form, you can find the roots of the parabola, which, if you remember, the roots are the x-intercepts, and the roots are the opposite number of whatever's here. So -3, 0, and +6, 0. And the reason that they're the opposite sign of what you had here, just to remind you, is if you plug in these roots, you're supposed to get 0 as the answer because they're on the axis. That's what the roots are. So if you plug in a -3 right here, then you'll have -3 plus 3, which will be 0, and 0 times whatever this is 0. If you plug in a +6 right here, 6 minus 6 is 0, so the whole thing will be 0. So if you plug in the opposite sign of what's there, it'll give you 0 as the answer, which means it's a root that's a point on the x-axis. Okay, that's it. We'll go over a lot more examples in class and kind of get any of your questions answered, but that's it for the video.